BC Calculus, Lesson 7.5, Logistic Growth. So, what's a logistic curve? We've talked briefly about this before. We introduced something into the wild, and human population hasn't quite peaked out yet. And it starts off slow, and then it takes off, exponentially looking. But there's this peak value up here. Can't get any further then. And that's what a logistic curve looks like. It's fairly common in nature, happens on a regular basis. Yeah, that's all I got to say about that. So, we'll label this, we'll play with this. But before we get into it, how do you decompose something into partial fractions? And then why, which I'll get to. So, if you haven't done this in a while, it's not too bad, just a little tedious. If the bottom is factorable, we can rewrite this as linear. A couple major points I forgot. Numerator has to have a lower power than the denominator. Otherwise, use long division. And that's if the powers are the same, or if the power on the bottom is less. So, after you've done this often enough, you start to get pretty good at it. Factor the bottom, 2x minus 1, and x minus 3. Common denominator, a times x minus 3 plus b times 2x minus 1 over 2x minus 1 times x minus 3 equals the original. Notice that I factored it on the fly there. I didn't take my time. We can now say, oh, well, clearly ax minus 3 plus b times 2x minus 1 has to equal x minus 13. So we have a little trick. We say, well, let's make x equal to 3. And if that's the case, we get a times 0 plus b times 2 times 3 minus 1 equals 3 minus 13. And I keep this in a line because I don't have a lot of space here. But we get 5b equals negative 10. Therefore, b equals negative 2. And then we say, hey, what if we made x 1/2? We'd get negative 5/2 times a plus 0 times b equals 1/2 minus 13. And actually, I feel like doing that one right now. It's negative 12 1/2, which is negative 25/2. And only do that because then it's easy to solve. Flip and multiply, flip and multiply. We should get that a equals 5. So the whole purpose is that we can rewrite f of x as 5 over 2x minus 1 plus negative 2 over x minus 3. Yes, you can put the negative out front if you're in the mood. I don't. So why would you do that? Well, now we can integrate it. Well, not just easy, but we can integrate it. It's usually going to be a natural log. You'll see that in a moment. So now we actually write it down with an integral. What if the numerator has a higher power? Well, you're doing 3x to the 4th plus 1 divided by x squared minus 1. So you go x squared minus 1, 3x to the 4th, plus 0x to the 3rd, plus 0x squared, plus 0x plus 1. you don't remember, 3x goes here, because 3x times 3x squared goes here, because 3x squared times x squared gets me to 3x to the fourth. Keep going, minus 3x squared. Change all the signs, because it's easier to add down. And we get 3x squared plus 0x plus 1. Let's go with a 3 plus 3 over here, because we get 3x squared minus 3. Change all the signs, we're left with 4. So we are actually doing the integral of 3x squared plus 3 plus 4 over x squared minus 1, because that's our remainder with respect to x. This original problem should have a dx in it. Naughty me. So I got to do the partial fractions things here, because otherwise I cannot find the integral of that very easily. We've got 4 over x squared plus 1 equals a over x plus 1, pardon me, x squared minus 1, plus b over x minus 1, which is a x minus 1 plus b x plus 1 over x squared minus 1. X equals 0, and I'm really going to do this one, pardon me, on the fly. X equals 1. We get 2 times b equals 4, b equals 2. X equals negative 1. We get negative 2a equals 4. A equals negative 2. Confirming my work. Looks good. So one more time up here. Keep blocking off my work. 3x squared plus 3 plus negative 2 over x plus 1 plus 2 over x minus 1 with respect to x equals x to the third plus 3x plus, I'll just slap it up front, minus 2 natural log of x plus 1 plus 2 plus 2 natural log x minus 1 plus c hanging out here at the end. But I got a little math to do. Leave the x to the third, leave the 3x, but we got 1 minus the other, and we can put it to a power if we want. I'm going to leave the power out of it, but we can factor it out. So we go plus 2. We take this one, it goes on top. Natural log of x minus 1 over x plus 1 plus c. What a shock to find that calculus can be so detail-oriented and make you crazy because there's a zillion little details to remember. I know, shocking. Here's a nasty one. It goes to 3 variables. So we get a over x plus 2 plus b over x minus 2 plus c over x minus 1 equals a times x minus 2 times x minus 1 plus b times x plus 2 times x minus 1 plus c times x plus 2 times x minus 2. This will take forever. I will give you hints. Set x equal to 2, then x equal to negative 2, and then x equal to 1. And you should get something along the lines of might mix things up here, so I gotta be careful. 3 over x plus 2 plus 1 over x minus 2 plus 2 over x minus 1, and we're finding the integral with respect to x. So we get 3 natural log of x plus 2 plus natural log of x minus 2 plus natural log plus 2 natural log of x minus 1 plus c. Wow. Which I talked about this before, we could have done and didn't. We can combine all these, are being multiplied, and you might say, well then, what do we do with the 3? Well, we can slap it up in a power and just let it go from there. X plus 2 to the third, x minus 2, x minus 1 squared plus c. So I left a lot of the busy work out just in the interest of time, but you get the general idea. So we started by talking about logistic curves. Now we're back. Here's a differential equation. Some thing k, constant, multiplied by p, where p is the population. But it has a maximum population. That's that curve we talked about. That's the limit up top that we talked about. I suppose I should call it a horizontal asymptote. And it always looks like this. Always. And the population at the highest growth is half the maximum. What's the growth at that point? Well, you have to plug in and get the, it's changing at 50 bodies per year, 40 animals per year, whatever. But that population, when it's growing the fastest, is half. That's a characteristic of every logistic differential equation. So now we're going to let you do some work here. What is the maximum carrying capacity for the wildlife preserve? Well, it's right there, m equals 100. What is the bear population when the population is growing the fastest? And that's what I just said. The population, I put a 1 on it. I'll put fastest growth. Is 50. I just put 50 bears. Now, the question is, what's the rate of change when it's growing the fastest? Like I said, you just plug it in. So dp dt equals 0.008. Population at that point is 50. And that's times 100 minus 50. And since this gives like an instantaneous rate, it's a little goofy, but you get the idea. It's increasing at 20 bears per year. So here's another example, and we actually want to solve the differential equation, which, I kid you not, it's a hassle. So This is a true story. 61 Canadian moose were put in the Upper Peninsula of Michigan. There's actually a moose population up there already, but it's in a separate location, and it had died out over the years. So they said, let's try a new one. They were hoping they'd get to a carrying capacity in 25 years, which they did not get to, but that's okay. According to this model, the carrying capacity is 1,000 moose. Slope field I'm not going to get into, just put in calculator or Desmos if you want to see what it looks like. And it's a big part of the AP exam, but just a little bit stuck for time here. And then it says solve the differential equation. So yeah, that's not easy. It is P equals the integral. We'll put in this later, so we'll leave the carrying capacity now. 0.0003P. Actually, I'm not going to write it this way. dP dt equals 0.0003P times 1,000 minus P. We will take this and do separation of variables thing. dP over P times 1,000 minus P equals 0.0003 dt. Math to do. Factor it, we get A over P plus B over 1,000 minus P. And that equals A times 1,000 minus P plus B times P, and that should equal 1. So that's what's on top of this fraction, despite the dP sitting there. If P equals 0, A equals 0.001. If P equals 1,000, B equals 0.001. Cool. No, that's wrong. No, that's right. So here's our differential equation we're going to mess with. Running very much out of space. Integral of 0.001 over P plus 0.001 over 1,000 minus P with respect to P, and that equals 0.0003 dt. Barely fitting that in. I'm going to skip to the end just because we're out of space. We're going to be, no, I'll write it out. We got dividing out the 0.001 makes life a little bit easier here. So natural log of P minus natural log of 1,000 minus P. Notice no absolute value because we know it's going to be positive because we know the real case. There's the 0.001 divided out plus C. Do some manipulation with the natural log here. By dividing everything by negative. And then doing that E thing, 1,000 over P minus 1 equals E to the negative 0.3T minus C. Flip our P, plug in our C, out of space, so I'm going to cut to the chase. And we get P equals 1,000 Hey, that looks like a familiar number. Over 1 plus 15.393 e to the negative 0.3t. And you say, wow, you skipped a lot of steps in there. How am I supposed to recreate that? And I say, you're not supposed to. It's going to be right here. All right. M is going to be your carrying capacity, max. A is going to be a constant. You'll get it from initial conditions. And K is also going to be a constant. They're both positive constants. So generally, we're going to give you all this. I am not going to go through this one just because I've gone long here. But again, this would be a logistic curve that you can use your calculator to model the data. If you do it right, you should get something like P equals 316440. Over 1 plus 23.577 e to the negative 0.1026t. And then you can play with it from there and answer any questions that pop up, such as these. That's it. That's a boatload of math. So good luck. And as always, happy mathing.